much more seldom used. So if you wind up having to use equation number 2 or number 5, and what we're going to do is this funnel is going to narrow. There's a lot of things that have to go wrong, so to speak, before a quadratic equation is the way to go. Because even then, in the last example, we ended up using equation number 2, solving for time, and we still didn't have to do it. We got lucky that the displacement was 0, right? So another thing that has to happen is that the displacement is not 0. So this is no level ground. I guess I'll call it unlevel ground. And you still have one more out. The other out is if you have no initial y velocity. Well then, 0 times t is 0, so then that doesn't appear, right? Then you don't have a t squared and a t, you just have a t squared. So that's easy. Solve for t squared, square root it, you're done. So also, the v initial can't be 0. Or, in the case of equation 5, v final. So only if all of these things are true, then use the quadratic equation. Okay? And of course, this example that I've just started doing is specifically designed so that we wind up in a situation where that's where we land. Okay? So we're asked for the time. It's equation number 2 that we end up picking. And then we're already at step 3 there, and we're hoping one of these two is 0, and unfortunately neither is. So off we go to quadratic equation land. Okay? So for those of you that just quickly don't remember, first of all, the equation needs a little bit of prepping. You need to move all the terms to one side. So don't forget to do that. It doesn't matter which side you pick, but they all have to be on the same side. The 0 has to be on the other side. Then you identify the coefficients, a, b, and c, and you put them into the quadratic equation. So this is at squared plus bt plus c equals 0. Maybe you've seen it with x before. It doesn't really matter what the unknown is. Okay? So t equals negative b plus or minus square root of b squared minus 4ac all over 2a. If you forget what that is, it is on the equation sheet. You don't have to memorize it. If you go ahead and do that, you'll get something around 3 seconds, and the other root is minus 2 seconds, which presents kind of an interesting thing because there's only one answer for the flight time, right? So why is it producing 2 answers? Of course, the nature of the quadratic equation is to produce 2 things. There will always be one positive answer, always one negative answer. The positive one is the actual flight time, and the negative one, throw it away. If you get 2 positive roots, you did something wrong. There's something wrong in your setup. If you get 2 negatives, definitely did something wrong. You should get 1 positive, 1 negative. The positive one's your answer, the negative one is not. Now, if you are careful to do all your math perfectly, and are sure that you're going to get the answers right, then the negative root is just trash. But I'll tell you something, it is useful sometimes. What is this time? Well, this time is your equation not realizing that time only can go forward. So it's actually extrapolating back into the past about what happened before t equals 0. It's extrapolating the rest of the arc. It's this. So what it's actually telling you is that we would have taken 2 seconds to rise from the ground level and be going at 5 meters per second when it's 30 meters high, and then it would have taken 3 seconds to complete the arc. Okay? So it's basically giving you information about the entire arc of which your flight is a segment of it. Okay. Now the reason I tell you this is because we already know that if you have a level ground flight, time up equals time down, right? So time from the bottom up to this should be the same as the time as this back down, okay? So if we already found that this is 3 seconds, there's no way this could take 12 seconds, right? So we know by definition that this and this should be equal times. And since we've split it up unevenly, the positive root should be larger and the negative root should be smaller. So if we get 3 seconds and negative 20 seconds, we know we did something wrong. Okay? That's just kind of advanced error checking. The negative root in this case should be smaller because our arc is broken up with more of it in the positive time and less in the negative time. Okay? Are there any questions on that? Yeah.
So if you were to ask, for instance, how long it was on the downward arc, it would be like 2.5.
How long it was on just from the here to here? I think that's right. Yeah, because this would be this would be an extra 0.5 seconds, and then this would be 2.5. Yeah, that's right. Because we know that the whole arc would be 5 seconds, and we can split it up 2.5, 2.5. So it would have taken 0.5 seconds to reach the top, and then 2.5 seconds to fall. And of course, the 0.5 and the 2.5 add up to the 3-second flight time we were looking for. So it's useful even in these unlevel ground flights to still think of it as being pieces of a bigger symmetric flight. Okay. So that would be like a trick. You could use a trick or something to get around, certain calculations or whatnot. Okay. So I think that takes care of these examples. Did quite a few examples here. I think I did 3 examples in a row of doing these constant acceleration equations. The first one was last time with a car. Then I just switched to acceleration, which is a handy constant acceleration that nature gives us. Obviously, we haven't talked about why yet, but it's kind of like jumping the gun a little bit on gravity. It's just a nice constant acceleration situation that nature hands us, so we can use it with our equations. And I did 2 examples with it. Actually, I think I did 3. Last time I did just dropping it. Now I did the level ground and then unlevel ground. That's kind of it. That's the only flights possible. Question?
Will these be on the level sheet?
Yes, I mentioned that they are already on there. Just the X ones, not the Y ones. And that's already available for you to preview. So I would recommend just printing one out and having it in the front page of your binder. All right. Next order of business, graphing. The 3 graphs we'll look at are position versus time, velocity versus time, and acceleration versus time. Something like that. Now, if you thought we were done with position, we're not, because position is something you have. You can index something's position. I can say at this time I have this position. You can't say that with displacement. Displacement is not something you have, it's something you do. I did this displacement. I started my displacement at this time and I finished it at this other time. So we want to only talk about quantities that are indexable with time. You can say you have a particular position at a given time. You can have a particular velocity at a particular time. You can have a particular acceleration. Okay? So these are all things that at any given timestamp, you can say that this object has them. Okay? Notice, by the way, how they're called. This is an x versus t graph. Okay? You say the dependent variable first and then the independent second. Okay? So your typical graph that you might do in math class is a y versus x graph. Okay? because the y is on the vertical and the x is on the horizontal. So I think to make this a little less abstract, I'm just going to jump in and discuss in the context of an example. I'm going to start with a position versus time graph. I'll put the units here so I don't have to put them on every single tick mark. And I'm just going to pick a shape. It doesn't really matter what the shape is as long as we then know, okay, this shape means this motion. Let me leave enough room for 1, 2, 3, 4, I guess 4 seconds on the time axis. And let me leave enough room for 1, 2, 3 meters on the x-axis, the vertical axis. And let me just pick a shape here. Doesn't really matter what it is, as long as we can look at that and understand what motion it's representing. So we go from 0, 0 to 1, 3 to 2, 2, and then 4, 2. Those are the coordinates. So let's draw a picture of what this graph is telling us. This is our physical x-axis that we're moving along between. So at t equals 0, where are we? X equals 0, so here we are. We start at the origin at t equals 0. You don't have to. The origin is just a reference point, but in this case, I am. Then after 1 second, where am I? 3. I'm over at 3 meters. Then after 2 seconds, I'm at 2 meters. And then I stay there. So I'm there from 2 to 5 seconds. So in essence, what this graph is telling me is that I walk one way, then I walk the other way, and then I stop and hang out for the last, what? Sorry, 2 seconds, right? This is 4. So this is 4. So I hang out for the last 2 seconds. Sorry about that. So that's just the raw information being given to me by the graph. I haven't inferred any information. This is just literally what the graph is telling me. But there is more information on the graph as well that can be inferred, not just handed to me on a silver platter. And one of those is the slope. So the slope of this graph, well, slope is rise over run. So in this case, the rise is how much your x value changes, and your run is how much your t value changes. And that should highly suggest what quantity? That's what kind of velocity? Average, right? The ab. So if I take the slope between any 2 points on this graph, it'll give me the average velocity between those two over that time interval. So let's go ahead and do that. I'll label my 3 kind of distinct segments, A, B, and C. So segment A, my average velocity, what's my rise in segment 1? What's 3, what? Meters, and what's my run? 1 second. So my average velocity during segment A is plus 3 meters per second. All right? So going from here to here, here to here, my average velocity is plus 3 meters per second. Makes sense. I had displacement of plus 3 meters in 1 second, so that was my velocity on average. I can draw in that sketch over here as well. I took this slope. Now let me point out that the graph didn't necessarily need to connect the way that it did. It could have some curvy thing. As long as the endpoints were the same, I would have gotten the same slope. So if you had some crazy looking graph like this, you're still finding the average velocity between these 2 points. You just take the slope between them. But, of course, we did happen to connect these 2 points in the simplest way possible, which means that the value we got for the average velocity wasn't just the value on average. If you took the slope and any given segment, no matter how small, you would have gotten the same value, which means that this wasn't just the average velocity, it was also the instantaneous velocity the whole time. So we could not only say that the average was this, it literally was that the whole time. Plus 3 meters per second, plus 3 meters per second, etc. So because of the shape of the graph, it's also the instantaneous velocity from the entire time interval from 0 to 1 second. And of course, since all my segments are like that, when I take the slopes, I'm not only going to find the average velocity, it'll literally be the instantaneous velocity the whole time. So, segment B, BAV, what's the rise in segment B? -1 what? Meter, and what's the run? 1 second. So that's -1 meter per second. As long as the graph had those endpoints, that would be the average. But luckily, when I took that slope, I wasn't just finding BAV, I was finding the velocity at all points during that. So this happens to also be the instantaneous velocity for this entire time interval. Now, first of all, it makes sense that it is negative because, of course, during that part, I was going in the negative direction, right? So if this was what was happening from 0 to 1 second, from the next second, I went like this. BAV was -1 meter per second, and it was literally that the whole time. That was what was going on from 1 to 2 seconds. I went to the right, then I went to the left. And segment C, that you can do by inspection. What's the slope? 0. So my average velocity was 0 there, and because it has the same slope throughout, that was literally what I did from 2 to 4 seconds, was just sit and do nothing. Okay. Okay. So just by taking the slope, I have been able to generate all the information about velocity as well. Let's go ahead and draw that graph. I'll do it below here just so that they line up. So my velocity value for the first second was plus 3, I think. 1, 3, like this. It was constant. Then, during the second, it switched to -1. Looks like this. And then it switched to 0. So you switch from one velocity to another to none. So that's your velocity graph. Now there is one thing that sort of breaks our rules on this graph. What is that? What's wrong with the graph? Anything? Anybody know? What's that? It goes. No, that's okay, because if you go from positive velocity to negative velocity, that just means you're going from the right to going to the left. Yeah. That's right, it's discontinuous. So we somehow went from +3 to -1 in no time, which of course is not really realistic. So we said that velocity values should be continuous. We can't have jump cuts, right? So this is a bit of an oversimplified graph. It's just meant to get us started. The next example will get us more something more realistic. So for us, x values have to be continuous, and b values have to be continuous, and only acceleration is allowed to have jump cuts, right? So for instance, when you're taking your foot off the gas and putting it on the brake, we're assuming that happens in a negligible time, but the velocity can't magically change, okay? So it's not to say that this is completely ridiculous. It's just that maybe the graph changes so rapidly that we neglect that. For instance, in a real life situation, if I'm walking to the right, I can switch directions pretty quickly to where you sometimes don't need to worry about the transition from one velocity to another. If you spend long bits of time doing one velocity and then switch very quickly and spend long bits of time doing another velocity, maybe you don't care about these transition zones, it's fine. But if we're playing strictly by the rules that we've set, we don't want to allow jump cuts in velocity, okay? So that's it for this example. You can see that we can generate from a position graph, we can generate a velocity graph as well. So whatever values are being plotted here, the slopes are plotted here, okay? So you're basically finding the slopes of the position versus time graph and then plotting them as values, which is the velocity versus time graph, okay? So if I go back over here to the master plan, it's going to turn out that anytime you want to move down to the next graph below, you take the slope. So the slope of a graph becomes the values plot. The slopes of a graph become the values plotted below. It turns out that it's also possible to reverse the process. If you want to generate the graph above, the reverse process is called area under the curve. That's how you work to the graph above. And for those of you that have taken calculus, you're seeing that I'm basically doing calculus without calculus. Obviously, we'll greatly restrict the complication here so that it can be done without any more new math. So slope, we have a fancy name for that in calculus, which is called derivative, and area under the curve gets a fancy name called integration or antiderivative. If that rings a bell for you, great. If not, don't worry about it. Okay, this is non-calculus-based physics, so we're not going to go nuts here. The next example I'm going to do is I'm going to start with this middle graph. And the reason is hopefully obvious. If I start in the middle, then I can not only show you how to move down again to the slope, so I'm going to take the slope of this and get this, but I'm also going to have a chance to show you the process of area under the curve to work up to this, right? So that's going to be my second graphing example. Let's see if we can knock that out. I guess let me go over here. Some of this stuff I want to leave on the board so I can compare and contrast. So here's my second example. Start with a velocity versus time graph. Again, it doesn't really matter what the shape is as long as we're able to correctly interpret what it's telling us about the motion. So let me leave 1, 2, 3, 4 seconds again, room for 4 seconds worth of travel, and then I'll leave +1, +2, +3, like that. And then I'll just pick a shape. Doesn't really matter what the shape is, just do we know what that shape tells us. Let me go ahead and do it. And it looks like I'm not very imaginative with shapes because I'm going to pick the same exact shape. Obviously, I have my reasons for doing it as well. The first thing I want to do is plot what this is telling me. All right. So what is this telling me? It tells me that at t equals 0, I have a velocity of what? 0, right? So at t equals 0, I'm at rest. Then my velocity turns positive, which means I'm traveling to the right, if I'm choosing right to be positive again, which I usually do at this point in the course. And after 1 second, I've achieved a velocity of plus 3 meters per second. T equals 1 second. All right. How about the time interval from 1 second to 2 seconds? Do I turn around? Velocity is still positive, right? So I'm still going to the right. Now my velocity is plus 2 meters per second. I slow down. Well, my velocity, all my velocity values are positive in this graph. So they're all to the right. Okay, from 2 to 4 seconds, do I stop? No. My velocity is just constant.